Hello class, today we are continuing our topic of electrochemistry with an introduction on how to classify reactions and determine oxidation states. So next we're going to look at the oxidation state of sulfur in the polyatomic ion sulfate. So what's important is that we first identify that this time we have a charge on the polyatomic ion and that charge is -2. In the previous example of dihydrogen sulfide, H2S, we had a charge of 0. So what we first want to do is draw a Lewis structure, which we have here, a sulfur in the middle, 3 oxygens around it. And when we fill in octets, we find that one of the oxygens must have a double bond to it, while 2 of the oxygens have single bonds, and then we need to fill in additional electrons for sulfur. And all of that is to get to the magic number 26. Where does 26 come from? Sulfur is a group 6 ion right below, or a group 6 element rather, right below oxygen. So sulfur also has 6 electrons when it is neutral. So we have 1 sulfur atom that has 6 electrons, 3 oxygen atoms that are each 6 electrons, and 2 additional electrons coming from that -2 charge. That brings us up to a total of 26 electrons. Those 26 electrons are present in our Lewis structure. So once we have our Lewis structure, we can see that each of the oxygens has a negative charge, which gives us our 2-. We are going to break the bonds, and this is just an exercise in which we consider the molecule as being completely ionic, so we break, in quotes, the bonds and move all of the electrons onto the more electronegative atom. The more electronegative atom in this situation is oxygen. So each oxygen now gets a full octet. All of the electrons from the covalent bonds have gone onto the oxygen atoms, and when each oxygen has 8 electrons around it, it is electron rich by 2 electrons because when neutral, oxygen has 6 electrons. So we have a total of 3 oxygen atoms with 2- charge on each one. If we were considering what the charge of sulfur is, we might suspect that it's a +6 in order to balance out these 3 2- charges, because 3 times 2 is -6. So we got -6 charge coming from the oxygens. You might expect that to be +6. However, we have a -2 charge on the compound. So what we can do is we can consider the charge by taking 3 oxygen atoms plus 1 sulfur is going to be equal to the charge of the molecule. 3 times -2 plus sulfur is equal to -2, which is our charge. So -6 plus sulfur is equal to our -2 charge. We add 6 to both sides, and we get a sulfur that actually has a +4 charge on it. So not +6, but 4. That has the overall effect of being, if this were neutral, it's +6, but there's a 2- charge, so it gets knocked down by 2, down to +4. So that's how we are able to figure out the oxidation state of each element in sulfate. It's 2- for each of the oxygens and 4+ for the sulfur. Next, we're going to move on and talk about classifying reactions as acid, base, or redox. First, we're going to take a look at sodium sulfide reacting with hydrochloric acid. So the first thing that should jump out to you is that we have a strong acid in this reaction. So the first thing to check is whether the strong acid is actually acting as an acid. How do you check that? Well, if we have a strong acid, it should be donating a proton, and something else should be accepting a proton. So in this situation, we have a proton, or hydrogen, with a +1 charge, which is a proton, bound to chlorine, which has a -1 charge. We then go over to the product side of the equation and see what was the fate of that hydrogen. Well, it ended up on sulfur. Sulfur here, as in an oxidation state, has a -2 charge, and each of the hydrogens has +1. We could have figured this out in the same analysis that we did back up in example 1, where we determined that the sulfur was -2 and the hydrogen is +1. So the hydrogen has gone from +1 to +1. It has remained a proton. So this strong acid has successfully donated a proton. The sulfur and has landed on sulfur. So the next thing to check is, did sulfur start as a base? Did it accept a proton? So sulfur here is -2. What was sulfur in the reactant? It was bound to 2, or paired with, 2 sodium ions. When sodium is not alone, it is a +1 oxidation state, and we know that from looking at the periodic table. The only time sodium is by itself is when it's 0. Otherwise, it's going to give up 1 electron each to become isoelectronic to neon. It gives up an electron, becomes a +1 charge, and ends up being as stable as neon, a very stable +1 ion. So we have 2 sodiums each of them has a +1 charge, so sulfur is a sulfide, -2. Sulfur has gone from -2 to -2, so there's no redox event there, and we just have a proton being transferred from hydrochloric acid to sulfur to make H2S. So overall, we have no redox event here, and we have a proton being transferred. That's an acid-base reaction. Next, we're going to look at an example that is a redox reaction with hydrochloric acid. So here, hydrochloric acid, we again have hydrogen being a +1 ion, chloride being -1. Now, what is the fate of that hydrogen? Well, in the product side, it's hydrogen gas. This is the only situation where we would expect hydrogen to have a 0 oxidation state because that is hydrogen in its elemental form. So we actually don't have a proton being transferred here. We have a proton in the reactants, but we have hydrogen as a product. So this is not an acid-base reaction because we haven't donated a proton to anything. So what has actually happened? We have a +1 charge being reduced down to 0. So that gives us a green dashed line, which I'm labeling as a reduction. If we have a reduction in the oxidation state, we must have an oxidation. So where is our oxidation event? Well, chlorine in hydrochloric acid starts as chloride. In the product, it's ending up as a salt with sodium ion, which also gives it a chloride. So chlorine is redox inactive. It's going from a -1 charge to a -1 charge. There's no change there. In the product, we have that +1 ion for sodium, giving us a nice and stable sodium chloride salt. But in the reactant, we have sodium in its 0 oxidation state because this is sodium metal in its elemental form. So sodium is going from 0 to +1. That is an oxidation. So we have an electron being transferred from sodium because it goes to a +1 charge, and it's getting acquired by a proton, which gets reduces down to 0. So this is an electron transfer event, which means this is a redox reaction. Next, we have a reaction between magnesium solid and chlorine gas. These are two examples of elements in their elemental form. Here we have magnesium as a metal all by itself. That's the only situation where you would expect magnesium to be a 0 oxidation state. Otherwise, magnesium would really like to give up electrons like sodium. But this time it would like to give up 1, 2 electrons to become isoelectronic to neon. So magnesium is very comfortable being in the +2 oxidation state, and that's exactly what happens. Magnesium gets oxidized up to +2. It is paired with 2 chlorines, each has a -1 charge to make this magnesium chloride salt in the product. So what's happening to magnesium? It is getting oxidized, it's losing electrons, and its charge is increasing. Chlorine, on the other hand, is beginning as 0, and it is being reduced because it's acquiring electrons from magnesium. So its oxidation state becomes more negative as it's going from 0 to -1. So we have a magnesium being oxidized, and we have a chlorine being reduced, and both of them end up in the same salt at the end. So here's a mnemonic device to help keep some of these redox reactions straight. So the mnemonic device that I prefer is oil rig. And that oil stands for oxidation is losing, and the thing that it's losing is electrons. When something loses electrons, it becomes more positive. So magnesium is losing electrons to become more positive. Rig, the second half, is reduction is gaining. When something gains electrons, an electron is a negatively charged particle, it becomes more negative. So in this situation, we have chlorine becoming more negative. Next, we're going to talk about balancing redox reactions under aqueous conditions. And this is a complicated process, and it involves balancing electrons and atoms. So we're going to take it step by step. In the first example, we're going to deal with acidic conditions. So first, we're going to take a look at is this complicated looking polyatomic ion called chromate. But we can simplify this reaction because chromate reacts with zinc, solid, to make 2 equivalents of chromium 3+, there should be a 2 there, that was a typo, and 1 equivalent of zinc 2+. So, other than chromate, this reaction that is redox is relatively straightforward. So let's analyze it. First, we need to figure out the oxidation states and redox pairs. When you have a metal ion that's by itself, its oxidation state is equal to its charge. So this zinc 2+ is a +2 oxidation state. This chromium 3+ is a +3 oxidation state. Zinc solid, which is the only situation where a metal would have a 0 oxidation state when it's by itself in its elemental form, has a 0 oxidation state. Now, let's look at chromate. So when we look at chromate, all we really have are a couple of chromium atoms aligned with a couple of oxygen atoms. So what's important here is that oxygen has an electronegativity of 3.5. That's actually pretty high. It is greater than all of the transition metals, and that includes chromium, which is located here. So when you have oxygen bound to any transition metal, what we're going to do is we're going to go through that whole process where we, quote, break the bonds, and all of the electrons are going to go to the more electronegative atom, and when that's oxygen bound to a transition metal, all of the electrons go to oxygen. So we don't actually need to draw chromate. All we need to do is assume that all of the electrons are going to go to oxygen, just like we did with sulfate. So when oxygen gets all of the electrons that it can have, it's going to have a full octet, and it's going to be a -2. So anytime you have an oxygen bound to a transition metal, you can consider that oxygen to have a -2 oxidation state. So let's do exactly that. Here we have chromate. If we have a -2 for our oxidation state for oxygen, what is going to be the oxidation state for chromium? We can use the same equation that we've used previously, where we set all of our atoms together, added together, equaling our charge. So we have 2 chromiums plus 7 oxygens is going to equal our charge. The charge on the complex is -2, and that's going to be equal to 2 chromiums plus 7 times -2, because -2 is our oxidation state for oxygen. So we have 2 chromiums minus 14 is going to be equal to -2. So 2 chromiums is going to be equal to +12. So each chromium is +6. So we've identified our oxygen oxidation state, which is -2, and our chromium oxidation state, which is +6. Now we can determine our redox pairs, since we've determined our oxidation states. So we have chromium beginning as a +6 ion, ending up as a +3 ion, and we have zinc starting as 0, ending up as +2. So zinc becomes oxidized. So zinc oxidizes because it goes from zinc 0 to +2. It has become more positive, so it has lost electrons. That is the OIL in oil rig. Oxidation is losing. It has lost electrons to become more positive. Chromium is being reduced. It's gaining electrons to lower its oxidation state. So we go from chromium 6+ down to chromium 3+, because it has acquired 3 electrons. So we have identified the oxidation states in redox pairs. Next, we're going to balance the half reactions, because we need to have an equal transfer of electrons. Must have equal transfer of electrons. In the zinc reaction, we're being oxidized by 2 electrons. In the chromium reaction, we're being reduced by 3 electrons. So it's not balanced. So if we take those 2 half reactions, we see that zinc is being oxidized by 2 electrons. So we have 2 electrons as a product. Remember, in the oxidation reaction, you begin with your element, you end with an ion at a higher oxidation state, and you're releasing electrons. So electrons are a product. If you're ever unsure about this, make sure that the sides of your half reactions are charge balanced. 2 times the -1 for the 2 electrons plus the 2 positives is equal to 0. So we have a neutral zinc on the left side, and we have overall neutral on the product side also. We have chromium, of which we have 2. So remember, we have 2 chromiums, so we actually need to multiply this by 2. We have 2 chromium 6 ions gaining a total of 6 electrons to form 2 equivalents of chromium 3. So we have a product of 2 electrons, and we have a reactant of 6 electrons. So this half reaction of zinc needs to be multiplied by 3. When we do that, we have 3 equivalents of zinc react to form 3 equivalents of zinc 2+ that release 6 electrons. Those 6 electrons are then acquired by 2 equivalents of chromium 6+ to form 2 equivalents of chromium 3+. So our electrons are now balanced. 6 electrons are being released, and 6 electrons are being acquired. In the next step, now that we have our electrons balanced, we can look back up to this reaction and say that something else is unbalanced. That something else is oxygen. There's no oxygen in the product. Now we have a few steps that we need to follow in order to successfully balance oxygens. So first, what we're going to do is we're going to write the half reactions, and we're going to balance the oxygens by adding water. By adding water, we're then going to introduce hydrogen atoms. We're going to balance those hydrogen atoms by adding protons. We're adding protons because we are under acidic conditions. That is directly connected to our conditions. In order to do this correctly, you must be aware of whether or not you're under acidic conditions or basic conditions because the problem's done differently. So, let's do it. We have chromate reacts to form 2 equivalents of chromium 3+. Now we're using that 2 because that's how many chromium atoms there are. So we have 7 oxygens on the left side, on our reactant side, and we have 0 oxygens on our product side. So we add 7 waters because each water gives us 1 oxygen. So we've added 7 waters to our product side. That introduces 14 hydrogen atoms. So we then balance the hydrogen atoms by adding 14 protons to our reactant side. Now we have chromate and 14 protons are reactants, and 2 equivalents of chromium 3+ and 7 waters are our products. Now, let's look at the half reaction for zinc. We're using the 3 in front of the zinc now because our zincs are now charged balanced, so we have to bring in those coefficients that we just introduced for the rest of the way. So we now have 3 equivalents of zinc reacting to form 3 equivalents of zinc 2+. There are no oxygen atoms in this half reaction, so we don't need to do anything else. The next step is to rewrite the full equation. In order to do this, it's a little tricky, so we have to be really clear about what we're doing. We are going to write the overall reaction, so we have to lump together the left sides of both of our reactions. So I've circled all of our reactants. So our reactants go here on the reactant side, and that's 14 hydrogen plus atoms, so 14 protons, 1 equivalent of chromate, and 3 equivalents of zinc. Those react to make our products, so put a square around our products to make sure that we get them right. And so on the product side, we have 2 equivalents of chromium 3+, we have 3 equivalents of zinc 2+, and we have 7 waters. And that is our overall balanced reaction. You can add up the charges, you can add up the atoms, and everything is balanced. Next, what we're going to do is take a look at example 5, which is an example under basic conditions. So here we have an example of lead hydroxide reacting with chlorate to form lead oxide and chloride. So let's start with lead hydroxide. So we have lead bound to 3 equivalents of hydroxide, which is this polyatomic ion. Turns out, since we're considering everything as ionic, the polyatomic ion actually does not matter a ton. And it overall has a charge of -1. We're going to react that with chlorate, which we'll analyze in a second, to form lead oxide and chloride. So let's take a look first at our lead hydroxide. So we can take each element, each atom, add them together to be equal to our charge. So we have lead plus 3 oxygens plus 3 hydrogens equals -1. So again, oxygens are a more electronegative atom. So oxygen's going to get a full octet, so it goes right to being a -2. When that happens, hydrogen is going to be a proton because it's not very electronegative, so it gets a +1 charge. And then all we're doing is we're calculating for lead. So we have lead plus 3 times -2 plus 3 times +1 is equal to -1, the charge on our complex. So we have lead plus -6 plus +3 is equal to -1, and we add 6 to both sides, subtract 3 from both sides, and we get lead is equal to +2. So lead is a +2 ion to begin with. Next, we're going to take a look at chlorate. So there we have a chlorine and an oxygen atom combined together with an overall charge, and that charge is -1. So we have chlorine and a -2 again for an oxidation state for oxygen. Those are added together to give us a -1 charge. We add 2 to both sides, and we get a rare situation where chlorine actually has a +1 charge. Finally, on our product side, we have chlorine by itself with a -1, so that's its oxidation state, and we have lead oxide. Again, we have lead plus 2 oxygen atoms is equal to 0 for our charge because lead oxide has no charge to it. So lead plus 2 times -2 is equal to 0, so lead in the product as part of lead oxide has a +4 oxidation state. So through all of that analysis, what we've just done is determined the oxidation state of everything in this reaction. Next, we're going to identify the redox pairs. So in order to do that, let's take a look at what oxidizes. So lead begins as +2 and ends as +4. That is a change. If anything changes, it must be part of the redox pairs. In this situation, the charge is increasing, which means that lead is being oxidized, because again, it means it's losing electrons from the oil rig mnemonic. So lead is oxidized, it goes from +2 to +4. What happens to oxygen? It stays -2 the whole time, so that's not part of the redox pairs, but chlorine gets reduced. It starts as +1 in a rare situation and ends as -1. So chlorine is being reduced because it is gaining electrons and its oxidation state is being lowered. Starts as +1, +1, ends as -1. And we're going to end there.